All right, welcome back and good morning. We're going to continue today with Industry 4.0. And before coming to the content, some organizational aspects. So as we discussed during the very first class, we're going to have one more guest lecture. Dr. Agnes Koschmieder is going to talk about how Industry 4.0 and the Internet of Things is going to change consumer patterns. Right now, we schedule that for December 15th, so that's 3 weeks from now. Then we're gonna continue the last part of the class next year. Basically, is still a little bit in flux. So the guest lecture of Stefan Kusterer, CTO of Conjun, that one is pretty much set. But I'm not entirely sure how we're gonna distribute the topics. This is just kind of what I'm expecting. We might change that a little bit. Then, just as a reminder, you can watch all of these classes also online as well on the YouTube channel. We stopped, I think, roughly at this slide last week, and we were talking about distributed systems, multi-core, multiprocessor operating system types, and we were talking about different versions of how this can be implemented. And one version is a master-slave architecture. So in this example here, we have 4 CPUs that are connected through a bus system, but not all 4 CPUs are treated in the same way. So there's one master CPU, and then the operating system can use the other 3 CPUs as slaves. Compared to the symmetric multiprocessor architecture, this is what most of us have on our compute devices nowadays, where in this case also we have 4 CPUs, but from the perspective of the operating system, all 4 CPUs are treated in the very same way. So this is why this is called the symmetric multiprocessor model. All 4 CPUs in the very same way as we had it here before with the master-slave architecture share the same memory space and also the same I/O devices. Then continuing from a scheduling perspective, now if an operating system has multiple CPU cores available, the question arises, how are we going to do the scheduling here? And this is very basic, very fundamental, also taken from the book of Tannenbaum. One basic concept here is time sharing. So imagine you would have 16 CPU cores. You would have a number of processes here on the left-hand side, different priorities. So you have 3 processes, A, B, C, at a priority of 7. Then what's going to happen here is with all of your CPUs here, you would take the first process here. So you basically have a FIFO here, first in, first out. You start with process A. You pick a CPU for process A. In this case, it's this CPU here, and then the next one would be process B. You want to pick this CPU, and so on. So you go through your entire list of processes, and what obviously may happen is that you have more processes that are in the running state, or that want to have access to the CPU. Then you have CPU cores available, and then it's up to the scheduler to pick the right CPU core. We're going to talk about scheduling a little bit more in the context of distributed systems today, how we actually can guarantee, not in a local system, but in a global system, that when a process sends a message from A to B, and let's say this is the process with the highest priority in the global system, that this message can be transferred from A to B, and let's say it has to go through some network to another node, that the node of the recipient will receive this message in the very shortest amount of time. Then, this brings us then to this architecture. So we have 4 nodes that are in this case connected through a switch. Each node has its own CPU, its own memory, and some network interface, and all of these network interfaces are connected through a switch. And in this case, you actually may have different operating systems running on all of these nodes. When it comes to real-time communication, you usually, if you have a network system based on Ethernet, and nowadays systems are mostly based on Ethernet hardware, you want to use or let me maybe ask this as a question, why wouldn't you use TCP/IP if you're interested in real time? Yeah? Yeah. Yeah. Correct. Correct. You have the advantage that you get the confirmation it has been sent, and if it has not been sent, you will keep trying. And this might take time and will then lead to collisions with other packets on the bus. So one way to go around that is to have a distributed clock. So you have a synchronized clock on all of your nodes, and then you time share the bus. So each node only gets a permission to send in certain time intervals. And therefore, you then usually use UDP as a protocol, kind of to increase performance, because you don't get the acknowledgement. And there's actually an open source implementation for that called RTNet. It was developed by the University of Hanover. But most real-time operating systems like VxWorks and QNX, they have their own versions of that, which is basically the same principle. So they time slice the access to the bus. And this way they can prevent from collisions on the bus. Obviously, this only works if you only have nodes using this protocol on the bus. If you have another, let's say if you connect your laptop to the system, suddenly speaking TCP, you're gonna be in trouble. Okay, therewith we are almost at the end of distributed systems. A few words on communication, sending messages. This is probably nothing new to you. So there's a distinction between when you want to send a message, you may use a blocking call, or you use non-blocking calls. So that means you send a message, and you either expect an answer or at least an acknowledgement that the recipient has received the message, and your thread, the calling thread, would be blocked after you call the send command. Whereas in the case of the non-blocking case, you would get the CPU back immediately, and then at a later point in time with a different command can then check whether the recipient has received the message or whether you have received an answer. This can also be done with an interrupt, as suggested here on this slide. This usually makes programming a little bit more difficult, but at the same time, there may be cases where you want to get the CPU back immediately to work on other stuff. And we'll see a little bit more of that later today as well. From a timing perspective, what you can see here at the top, this would be a blocking call. Let's see, so sender is running, and here the sender would be blocked at this time, and then in case B, the non-blocking call, we would not be blocked. Now slowly transitioning from here to what we would use in DDS or in middleware concepts in general. There's also the concept of a remote procedure call. So when you when you call a function, you may have the object that you use for this function stored locally, but you might also have the object that you want to call the function for sitting on a remote machine on some remote node, but the function call pretty much looks the very same. And in this case here, let's say we have two machines, machine 1 and machine 2, and we have one process that calls a procedure on machine 2, then we would call the procedure here, return the result, and then we would continue here. In this case, this would be a blocking call. And there are a number of middleware concepts. Actually, the very first middleware concepts like Corba are based on this principle. It's fairly simplistic, but it has a number of disadvantages, specifically when it comes to making things real-time capable. And we'll talk about that in a little bit. And yeah, this is just a visualization of what I mentioned before. So having a conventional procedure call, so you have some function running locally, some process running locally, calling a function, the function is implemented locally, all the variables, everything is in memory locally. And if you have a remote procedure call, you call the function call here looks the very same, but through the middleware through a middleware like Corba, the middleware then managed to execute the function actually on a different machine. Yeah. Why do you think they would need to be stateless? No, I wouldn't say so. It doesn't have to be stateless. Yeah. And this is also one reason why when it comes to real-time and determinism, it makes it very difficult. Let's say you have a server running on one machine, and then you have two other machines where you have clients running, and now client A is going to access the server, and client B as well, and now the ordering might get confused. So maybe the programmer intended that the first machine has to call the server first to change the state, and then subsequently the second machine, the second client, should call the same server. And because the middleware or your network is not real-time capable, these two messages these two remote procedure calls get swapped. And now you actually get a different result. So it's a very non-deterministic system, which is coming back to the question of safety, what we discussed last week and the week before. This is definitely something that you want to avoid. But at the same time, there may also be cases where you actually where you don't care about that behavior. And I think web server are probably a fantastic example, because let's say if all of you would access one website at the same time, let's say the website even has a state, you would not really care about that. Let's say there's a counter on the website and all of you would just get a different number, for instance. Okay, other questions or thoughts, comments? Okay, if that's not the case, oops, why can't I continue here? It's weird. Okay. Yeah, steps in making this remote procedure call. So one thing to mention here is what all traditional middleware solutions offer is the concept of stubs. So you have let's say here you have a server system, a client system. They're connected through a network. You have your operating system, and then you have a server stub and a client stub. This is, and the stubs may be implemented in different programming languages and even running on different operating systems, which gives you a lot of flexibility when it comes to implementing such features. The most important thing is, in this case, that the stub, the API, so the stub describes the API, that the API is going to be the very same, and you don't really care whether it's implemented in Java, in C, or in something else. So you've seen that before. This is just a different illustration of what we talked about last week already, just to remind everyone what a middleware is. So we may have 4 different machines actually running 4 different hardware platforms. So 2 Intel architectures, a Spark, and then we have a like an Apple type of. This is like from the old days when Apple still had their own CPUs. You have different operating systems. You have your middleware, and now you have one and only one API for applications. So the middleware, again, it's a thin layer between the operating system and the application, and the middleware might run on different operating systems. What you usually do when it comes to real time, and now doing the transition to DDS, usually you would run the very same operating system on all of the nodes. In theory, I'm not sure whether this is done in practice actually. In theory, you can use different operating systems, different real-time operating systems on different nodes. And in theory, the behavior should be the same. And maybe there are cases where people have done that. In most cases, however, you use the same operating system for all of your nodes. Now coming to Corba, one of the features of Corba is that you have an object request broker, ORB. And Corba is the abbreviation for Common Object Request Broker Architecture. So here, the middleware, actually, let me display it here. So you have your operating system, you have a client ORB and a server ORB, your adapter in quotes, and then you have your stub here, or sorry, it's called skeleton here for the server side, and then your stub here on the client side. And everything now that's related to the middleware, everything that's related to Corba is shown in gray, right? So you have your one entity here, one entity here, and actually in most cases, on both actually on all machines, the ORB has server functionality and client functionality at the same time. And then you have your processes, which may be servers, which may be clients, communicating and exchanging information through skeletons and stubs with the ORB running in a distributed way on multiple machines. But in the only reason why I'm mentioning Corba here is this is kind of, there are still many systems based on Corba. However, in the context of Industry 4.0, Corba is not used at all anymore. It just leads to a very non-scalable, fairly messy architecture. You don't have any determinism, no timing guarantees. There have been efforts. The most prominent is called ICE, that have tried to slim down Corba and kind of implement a real-time version of it, because it's such a simplistic concept. Nothing really has made it into, at least not at scale, into products. So this has remained very experimental. So instead of implementing our middleware with remote procedure calls, we're going to talk about something else today, so that that we can meet the requirements for industrial automation. And here are just some of the requirements. We're going to see some more later today. If you think about safety again, determinism, reliability, what you actually want to see in implementations for industrial applications is having a distributed synchronization. So I mentioned already having a distributed clock, so that all nodes in your network do have the same time. You don't really want to have shared memory. Makes things very, very messy. Also, if you have a distributed system, the concept of shared memory would not work anyway in real time. Then you may want to have, and this is obviously application dependent, a feature to do mutual exclusion, and you want to do that in a centralized approach or in a decentralized approach. And mutual exclusion, so one example there, let's say you have a motor controller, and you implement the motor controller as a subscriber to a message, and the message is called set position or set velocity or something. Let's say, yeah, let's say set position. And now you have a number of publishers, and if you have 3 publishers all publishing this message, set new position or set position, and they would all, let's say all publishers want the subscriber, that is the motor controller, to go to a different position. The motor controller would be totally confused, right? It would get different set points from all of the publishers. So what you want to have is a feature that a publisher, or let me phrase it differently, that a subscriber can receive messages from only one and only one publisher. So that means if there's one publisher that that wants to send the message set position, that publisher needs to first request for permission. Hey, I would like to send this this message. Gets a token, sort of a password, and every time the publisher then wants to send the message, it has to add the password. And the middleware will then make sure, let's say there's a second publisher that also wants to send this message, that it will not be able to do that, so it will not get the password. Unless, of course, the first publisher gives the password back, which also means the first publisher will not be able to send that message anymore. And if then the second publisher wants to send that message, it will then get the password to then be able to send. For transactions, you want to have multiple operations, being able to also commit or abort. And timing here, specifically with abort, is the most critical aspect. So when you send a message, and let's say something goes wrong, whatever it is, a deadline is exceeded or expired, or something else goes wrong, you want to be sure, as a calling thread, that even if you don't get the message, get the reply that you want to be woken up again after a given amount of time, so that you then can initiate something to abort the system to fail safe, for instance, coming back to the topic of safety. And then when it comes to concurrency, there's something that's called two-phase locking. Actually, this is something we could talk about here in this context as well. I don't have a single slide on this. I might add that later, because this is another important aspect. Then some other things, a few of them I mentioned already. So event ordering. So if messages are sent in a certain order, we want to make sure that the messages are received in the very same order. We talked about mutual exclusion, atomicity, meaning that you want to have some operations that are atomic. So if you call an atomic function, you can assume that while calling this function, the CPU will not be taken away from you. So it's guaranteed that once you call that function, during the execution of that function call, you will keep the CPU no matter what. Yeah, concurrency control. We'll talk about that. I think I'm going to add that maybe for the week after the next to talk a little bit more about that, because that's an important aspect. Then deadlock handling, something very important. If you have a single node and the operating system, let's say you don't have a middleware, the operating system then has full access to everything that's being sent and received in terms of messages, and would be able to detect deadlocks. A deadlock meaning you have clients and servers. Let's say you have clients and servers A, B, C, D, and client A, which also happens to be a server, sends a message to B. B then, as a client, sends a message to C, C then as a client sends a message to D, and D then sends a message to A. So we would have a deadlock in that case. And now the middleware, because the middleware has access to all of the communication procedures, what is implemented inside of the middleware is a graph, and what you for each message that is being sent, and then you're looking for loops in that graph. And if you are about to close a loop, you would then send an error message back, basically telling the sender, hey, you cannot do that, because if we did this, we would have a deadlock and we would be stuck. And this now becomes possible because the middleware has access to all of the communication processes. I'm going to skip election algorithms. This is for redundancy. Then obviously determinism, a determinable worst case latency. And this is just to remind everyone, real time does not mean fast. Real time only means deterministic, being able to determine a worst case latency. And yeah, we talked about exclusivity. So focus now in this course is DDS. We're going to start with DDS now, and then I'm not sure whether, I hope that I'm going to finish today, but let's see. Otherwise, Stefan will continue next Friday, and then he will introduce details, technical details, specifically from a software perspective on OPC UA. At a high level, the reason we're talking about these two specifically is that DDS, or the concept of DDS, which is an open standard, is extremely powerful for everything that's happening at the lowest layers, like almost at the sensor level, at the actuator level, where you have maybe thousands, hundreds of thousands of nodes being connected through some network, and having these nodes being able to communicate with each other in real time. And this think about sensors, actuators in some plant for industrial manufacturing. Let's say some plant at Mercedes-Benz to manufacture cars, and literally all of the actuators and sensors that you have there obviously somehow have to communicate with each other. And traditionally, all of this has been done through very old school PLC systems. And the ones of you who have attended the real-time course in the summer term know that the concept of PLCs is obviously very outdated. I mean, this is really technology literally from the 60s and 70s. And with modern software approaches like the one that we're going to talk about today, you actually can simplify and speed up things tremendously, and also reduce costs quite tremendously. Now what is happening, DDS was developed for that purpose. And the weakness of DDS is when it comes to the higher layers, when it comes to non-real-time aspects, sending large amounts of data from A to B, having a modular concept for security, having a connection to the cloud. And this is where OPC UA comes in. So this is the strength of OPC UA. And what happened was, or what is happening, obviously, both of these players, I mean, obviously both are open standards, but while DDS is trying to get better at the higher layers, OPC UA is trying to get better at the lower layers, specifically when it comes to real-time networking. And people notice that neither works very well. And so there are more and more efforts. So it's going to be an interesting game that we will probably see in the next 5 to 10 years. People are now starting to build bridges between these two. So with the goal to get the best out of both worlds, kind of have an intermediate layer, and everything below this layer is going to be DDS, and everything above is going to be OPC UA. And that's the main reason why we're covering both here in this course. Okay, so I brought, this is again some slightly biased video with a little bit of marketing touch. So it's a 3-minute video introducing DDS. I'm gonna take off my headset so that you can listen to the sound as well.
Hi, my name is Rick Warren. I'm an engineer at RTI, and today I'm going to give you a brief introduction to RTI Data Distribution Service, our real-time middleware for high-performance distributed systems. RTI Data Distribution Service provides a peer-to-peer publish-subscribe communications bus for tying together many types of real-time and non-real-time information, including high-volume streaming data, complex events, sensor readings, or video. It's used widely in many types of applications, including military command and control systems, financial trading platforms, unmanned vehicles, and medical devices. RTI Data Distribution Service is built from the ground up on a foundation of open standards, which means you don't have to worry about being locked into proprietary software. In particular, the DDS programming interface from the Object Management Group provides portability across middleware implementations, while the RTPS network protocol, also from the OMG, provides seamless interoperability. RTI Data Distribution Service is the leading implementation of these specifications, and in addition to high-performance communications, it provides persistent reliability, visual design and debugging tools, data recording and analysis, and rich integrations with enterprise systems from spreadsheets to databases to application servers. Let's see an example using the RTI Shapes demo. This demo represents different streams or types of data using different shapes and colors. You can imagine that in a real-world system, these might correspond to moving vehicles, changing stock prices, or other values. Each window represents an application that could be publishing data, subscribing to data, or both. First, we'll publish a simple shape in one instance of the demo and subscribe to it in another. You'll see that I'm changing a couple of settings here. You'll find out what these do in a moment. As you can see, every change in the shape's position is reflected in the subscriber. We can start any number of subscribers to the same data source. Notice that we don't have to start any servers, it all just works. Now I'm going to pause the publisher. As you can see, the subscribers are no longer receiving data, so they'll pause too. But when I start publishing again, the subscribers immediately recover. In a real-world system, you'd probably want to have redundant data sources to serve as backups in case the primary source goes down. This is easy to do too. Let me start a second publisher. I've configured this data stream so that the subscribers will only receive data from one of the publishers at a time. But when I pause that publisher, they'll immediately fail over to the backup. When I resume the primary publisher, the subscribers will immediately resynchronize with it. You can find a lot more on the RTI website.
All right. So if you wanna play with GDS, one thing I can recommend is going to the RTI website and just download this demo. You can install it in a few minutes. It's really not a big effort. And actually, without even writing code, you can just open this demo and play with it. And they also provide a whole bunch of examples, sort of like a playground where you get a whole set of examples, including this one. And then just can modify it and play with it. And obviously it also works on non-real-time systems. So if you use a Linux or Windows notebook, it will also run on your notebook. Obviously not in real time, but conceptually you will see what's going to happen there. Some references to literature. for today's class, there's a fairly nice DDS tutorial that you can find here. That actually is provided by a company called AD-Link. AD-Link just acquired PrismTech, and PrismTech was one of the two bigger implementations of DDS, and the biggest one is the one by RTI. And you can find the documentation and under this link here below there. Everything is online. With a little bit of history, there are, and some of the papers are actually referenced here, some scientific papers, like how can you actually, from a scientific perspective, guarantee real time in a distributed system. So we will talk about a few concepts today, like more from a theoretical perspective, how you're actually going to do scheduling. And this is a paper from 2003, from the early days, fairly easy to read. So it's really not a heavy heavy paper where you need like a whole bunch of pre-knowledge, just to get a conceptual understanding of where DDS comes from. And then there are some further tutorials. There's the OMG website. Let me see, where's my mouse pointer? The OMG website, and obviously the RTI website. So with under this getting started thing, you can find also the software to download. Just as a reminder, middleware, thin layer between the operating system and applications. And starting with a little bit of history, the origins actually go back to Stanford University. There was a guy, his name was, or is, Stan Schneider, and he, in fact, he did his PhD in the same lab where I worked until like 4 years ago, roughly. And he, in the late 90s, then founded Real-Time Innovations, and at that time he worked mostly for as a government contractor to develop a software system for military applications. And unfortunately, in the United States, this is how it works. If you want to get funding for research, DARPA is your friend. And in the case of robotics, so we have never accepted any funds from DARPA just for the sake of not working on military applications. But if you're interested in getting significant funds, that's an easy way to go. And so he started with a distributed real-time middleware for military applications, and at the same time also contracted by the US government, a company in France, the Tails group, working on the same principle. So there were these two implementations, and at some point these guys had the feeling, okay, we are really onto something here. This concept really works well. It works much better than everything else out there. And they were actually interested in getting competition. That sounds weird, but in order to create a healthy market, you actually want to have a competitor so that customers can actually see, okay, there's some momentum behind, and if this one guy fails, I still have this other guy, or maybe even a third guy. And so they made this an open standard, and this open standard, I think that development started in about 2001, and then in 2004, this got approved by the Object Management Group, and then was first used for defense and aerospace applications. And now there's the fourth iteration of the standard, was just released in 2015, version 1.4. And today, there are several implementations, and the three big ones worth mentioning are OpenDDS by a consortium called OCI. Then there's the RTI version, the RTI implementation called Connect DDS, and there's PrismTech, or nowadays AD-Link with Vortex OpenSplice. So all three implementations follow the same standard, same APIs, same concepts, just different implementations. I have not worked with OpenSplice yet. I've worked with OpenDDS and DDS, and I can tell that I would recommend OpenDDS only for hobby projects. The quality, reliability, in many ways, in terms of timing, determinism, and just the number of crashes that you experience is orders of magnitude higher with OpenDDS. So it's significantly less professional than Connex DDS and Vortex OpenSplice. Now, giving an overview of what DDS actually is, the basic idea. Let me actually start with this image here. The basic idea is you have a global data space, which means you have sort of really think about objects here. So it's a very object-centric approach, and from a global perspective, really looking at your entire distributed system. For every application, it looks the same. It really looks like this. This does not mean that every node contains all of the data. So every node only has the data available that it needs to know, but we're not copy and pasting data to all nodes just to have it available everywhere. And then it's purely based on a publisher-subscriber mechanism. So the way it works is, in order to get started, you first need to start with a subscriber. And let's say the subscriber, let's use the example of a motor controller again. Let's say the subscriber is a motor controller, and the motor controller receives, let's say, a velocity set point for the motor. And then the subscriber registers this as an object or as a message, so that the middleware knows, okay, this guy understands the message or the topic, set position or set position motor control. You can name it whatever you like. And we'll talk about topics in a little bit more in a little bit. You can then add a number of features like exclusivity. So you can, for instance, limit the number of publishers, and you can limit it to 1. And once that has happened, then a publisher can start sending messages. And maybe you then have a second publisher, maybe even from the same process, and that process then offers a topic, get motor position. So for that topic, obviously, just reading out the motor position, you don't need to limit it to 1, right? So you can have as many people asking for the motor position as possible. So if then someone wants to know the motor position, if a publisher wants to know the motor position, it can send a topic, get motor position. That would be one way to implement it. What can you imagine would be another way for the topic get motor position to implement it? Yeah. Yeah. So instead of polling for it, you can just have a publisher that periodically sends out the motor position. And depending on your overall system, there's no right or wrong, right? So you really, as a developer, need to decide what's the best architecture for your concrete application. So to now come back to the slide here, and I'm going to read a little bit just from the slide. I think most of these things are obvious. So it's a high performance, and high performance in this case meaning low jitter, low latency, and when it comes to real time, having a worst case, determinable worst case latency if you want to send a message from A to B, but not only having it determinable, but also having it fairly low. Because this is, as a user, this is what you're interested in, right? You want to send a message from A to B. Of course, you want to get a guarantee that it will be arriving at B within a certain period of time, but you also want this time to be as short as possible. And this is, by the way, one of the big differences to Corba. So with Corba, you do a lot of copy and pasting. So you had the example with larger amounts of data. And you will have, in the case of Corba, we'll have copies of that data everywhere. And that makes it slow. Whereas here in this case, obviously you may have to copy data, but it's implemented in a way that you minimize copy operations, for instance. So it's data-centric, and it's, as I mentioned, a publisher-subscriber middleware. You want to have the right data at the right place, at the right time, all the time. And all the time now referring to high availability and reliability. Fully distributed, multicast enabled, high performance, highly scalable, high availability, hot swap, and hot architecture. So meaning that you also want to be able to add nodes during runtime. You want to add subscribers during runtime, add publishers during runtime, and also remove them during runtime. So this is a big difference to AutoSAR. So I'm not going to talk about AutoSAR in detail here in the context of this course. So AutoSAR is this middleware for automotive purposes. Who of you have worked with AutoSAR or at least know what AutoSAR is? This is, okay, fewer than I had expected. So AutoSAR is a static middleware that was developed for communicating within the car. So within the car, you have like multiple control units, and they all communicate through different bus systems. And the idea now is you have a real-time operating system, usually OSIC, and which, by the way, is also a static real-time operating system. So the static meaning that during compile time, you determine when each process is going to be executed. So during runtime, everything is already fixed. There's no, you cannot just add a process or remove a process. That the entire timing, the entire scheduling is already set during compile time. And that's very different here. So here things happen during runtime. So what are some features that now DDS will have to offer just to make sure that it keeps running robustly when all of these things can happen during runtime? Because obviously, if you keep registering topics and topics and topics, at some point you might run out of memory, or at some point you might not be able to guarantee timings anymore. What are some things that you think would be definitely required in this case? Yes. Yeah, that's one feature, and that is definitely implemented. I mean, otherwise you don't want to run out of memory. Other ideas? We will see a little bit more later when we talk about quality of service. So the middleware also needs to detect when you're going to miss a deadline. So if you kind of keep registering topics and topics and topics, and then you have publishers just throwing messages at the system, the system then will have to have two important properties at that point. Imagine a very simple scenario. You have one publisher, one subscriber, and they have a high priority message, a high priority topic that they are exchanging. And let's even say they do that at a not super high rate, something that you can easily manage on your hardware. And in addition, you now have hundreds, or let's say thousands of other low priority publishers and subscribers. What would you expect now from the system? How should it react when it comes to the high priority topic? And how should it react if you keep registering more and more low priority topics? Yeah. You probably don't want to drop data, but you want to notify the sender that you cannot handle this data anymore. You have to drop it because there's no memory capacity anymore to put it in your queue. So actually, sorry, I shouldn't say that. So dropping data is correct, but it's not only dropping data. So it's dropping data plus telling the sender, hey, I can't handle your message anymore, your topic anymore. No, the behavior that you want to expect here is that the high priority topic, and specifically the timing of the high priority topic, will not change. So even if you have a CPU load of 100% everywhere, like fully, everything is all of your resources are being used, the timing of your high priority topic must not change. And then for all of the low priority stuff, you want to expect exactly what we just discussed. So if there's an overload, let's say obviously there are buffer mechanisms, and then you have like a FIFO buffer, and if you have like a buffer overflow at that point, you want to acknowledge the sender. Then continuing here on the slide, blending data-centric and real-time publisher-subscriber technologies, content-based, content meaning topic here at this point, content-based subscriptions, continuous queries and filters, then fine-grained policy-based, and now we're coming to quality of service, policy-based tuning of resource usage. So for instance, you may want to restrict the amount of compute time that a publisher or a subscriber used. Then data delivery, we're going to talk about quality of service here, and you want to optimize for networking and computing resources, and quality of service, or maybe before going into details, what is quality of service for you? Yeah? And we will actually talk about a dozen features like that. And now, depending on your application, maybe you have some publishers, some subscribers, which very often are like controllers in let's say some manufacturing environment, and they may all have different requirements. So if you have, let's say, something safety critical, you want to make sure that you maybe have three publishers, for instance, all providing the same data just from 3 different sensors. And if one sensor fails, or if one process here crashes, you still have the other 2. And then you want to have the middleware being able to, as a subscriber, make sure that you at least get one and get a guarantee for that. That could be one example. Another example could be you need to get the response in a certain amount of time, because if you don't get the response in that amount of time, you actually don't need it anymore. And yeah, we'll talk about more of these. And then taking into account, and this then at some point makes it complex, all of these different features that can be customized for your application, you still want to optimize for networking and compute power so that your system remains scalable. Yeah, plug-and-play architecture. So I mentioned you can add publishers and subscribers during runtime. You can also add nodes, and adding nodes meaning you can add further entities of the middleware, further entities of DDS to the system during runtime. And the core aspects that are really distinguishing the DDS standard from others is that you have this highly data-centric approach, and that you at the same time can specify so many quality of service features, so many options for quality of service. So looking further into further under the hood here, at a very high level, you have two layers within DDS. The the lower layer, and that's actually where you handle all of the quality of service features, is called the data-centric publish-subscribe layer, DCPS. And this data is being used to exchange data between publishers and subscribers, and doing that according to quality of service policies. And every publisher, every subscriber can determine what quality of service one is interested in. It can be time, it can be resource constraints, it can be related to data usage, to network bandwidth, and more. And yeah, we'll see more about that later. And then the second layer is the data local reconstruction layer. This is the layer that then provides the data to the application in the format that the application needs. And this can, not necessarily, but this can be literally having a local object in cache, so that objects can access data of a topic as if it were local. Now the specification, the standard of DDS, only defines the interfaces and the policies. So policies meaning quality of service again, and then the software interfaces between the application, so the stuff that you would be implementing, and the middleware, the DLRL. It does not address protocols, techniques for different actors implementing the service. So that means by default, if you download the trial version from the websites, obviously you get support for UDP, for TCP communication on a network. Probably some, let's say for QNX, you would have synchronous message passing. For Linux, you would have some asynchronous message passing. Then for Windows, maybe some COM or DCOM based way to locally communicate. But let's say for your specific application, you have a new field bus, be it Ethernet based or something else. You can then also implement your own network protocol. You can implement your own specific UDP protocol, like a modified version of UDP. So this is not part of the standard. So you can implement anything you like to actually implement the actual communication from A to B. And the standard also does not specify how to manage internal DDS resources. And this is now where the implementations actually distinguish or differ from one another. So to dive a little deeper here, so I mentioned UDP. UDP is something that you get off the shelf, and then you have these two components here. You have the data-centric publish-subscribe layer with this minimum profile there. You also get this interoperability wire protocol, difficult word, that you also get off the shelf. And this is just one implementation that you may or may not use. I mentioned RTNet at the beginning. So this is sort of something like RTNet, which does the time sharing on the bus to make sure that when one node on your bus sends something, that no other node is sending something at the same time. So in the DCPS layer, you then have your profile. This is where you then actually specify your global data space. And there you also, now we have 3 entities here, ownership, durability, and content subscription. This is where you manage the quality of service, and where you, depending on what the application actually needs, make sure that this is guaranteed. And if it is not guaranteed, which may happen specifically because this is done in a dynamic way, if it is not guaranteed, or if you cannot guarantee it anymore, you have to notify the application, hey, I can't do it. So that, and this must be guaranteed, that if the middleware can't handle what it's supposed to handle, it has to acknowledge the application saying, hey, I can't do it. And then you have the data local reconstruction layer, DLRL, where you then do the mapping of the data of the object for the application. So the two components here, DCPS, DLRL, and the implementation obviously is language independent, so you can implement things in different languages. It's OS independent and also hardware architecture independent. So it might run on an x86 platform as well as on an ARM platform, on a QNX system, as well as on a safe RTOS system. Any questions? Okay. Let's continue. So I mentioned the data space, which is fully distributed. So you can assume that no matter on what node you are, virtually you have access to, although you might not have a copy available, you virtually have access to everything that's there. And obviously everything that's there are all the topics that are registered. Yeah, publishers and subscribers can join and leave at any time. So this is the dynamic aspect of it, and they express their intent to either produce or consume a specific type of data, and this is what is called a topic. So we're going to see a little bit more on that in a bit, like here. So subscribers and publishers and subscribers actually are matched by taking into account account topics. So if no topic has been registered, obviously no one can really communicate with the middleware. The only feature that is available is registering topics. But you cannot just blindly send a message to the middleware, because the middleware would have no idea what to do with it. So you first have to register it. And if then a publisher sends something, subscriptions are dynamically matched, and data flows from wait, does this make sense? Subscriptions are dynamically matched? I don't know what I wrote there. There's something missing. So subscriptions are dynamically matched, meaning that if you have multiple subscribers for one topic, the middleware will make sure that all subscribers will get that message. The middleware will also be aware maybe at what priorities these subscribers run. So there's the concept of using static priorities and also dynamic priorities. We will talk about dynamic priorities here in a little bit. If static priorities are being used, and this is also part of quality of service, then the middleware will also make sure that the subscriber with the highest priority will get the message first. Then a topic is a unit of information, usually an object, that is exchanged between the publisher and the subscriber. And there's an association between the name, the type, and the quality of service setting. And regarding quality of service, we will go into more details, I think, after the next slide. And then there's the topic type, and the type of the topic then describes the data that is associated with it. And this can be described in IDL, the interface description language, or also in XML. There are also some, like for the most common data types, there are some features that come off the shelf. So let's say if you want to use an integer or floating or a Boolean variable, you actually do not have to implement XML files. You can just use things natively. And yeah, the topic can be represented by an arbitrary number of attributes. So you can even have large complex objects of any kind that you can handle as well. But for those, obviously, you will need to represent them in IDL or in XML. So looking a little bit under the hood, the entities for DCPS, data-centric publisher subscriber. You have the topics, this the type data that we just discussed. You have the publishers, which write data. You have the subscribers that read data. And then you may also specify specifically in more complex applications, you want to use domains. So the advantage of domains is that this is something that can speed up your system quite tremendously. The idea of a domain is if you know in your application that you have a publisher and a subscriber both running locally, you obviously then can also implement some local communication mechanism outside of the middleware, so that the middleware is not aware of what's happening. You may even use shared memory or whatever you like. But that's not elegant, because then you have multiple communication APIs and your code actually gets pretty messy fast. And with the idea of the domain, you can now tell the system, hey, this is the domain, and it's sort of a subsystem inside of your bigger system. And specifically, if the domain is running locally, that also means that the middleware does not even have to distribute that. So the middleware knows that everything that's happening here inside of this domain can be kept locally. So only local communication is necessary, and that speeds up the entire process, so that actually locally you can even have cycle times of something in the range of less than 100 microseconds on modern hardware. Then yeah, we talked about blocking, non-blocking calls. So there's wait-based calls, synchronous calls, and listener-based calls, asynchronous callbacks, and we'll talk about that in a little bit as well. And then there is a way to also filter things, so that not everything is going to be available everywhere, and you can for more advanced applications you can filter topics. And then again, the key feature of all of this is, for every topic, you have different quality of service features available. So I think I can skip this one. This is something that we talked about. Let's start with quality of service. This is a slide that I pretty much copied from the standard. And we're going to go into some of the details here. So these are all of the quality of service options that are being provided by DDS. And at a high level, we can distinguish between features that are concerning data availability, data delivery, data timeliness, resources, and configuration. And we're going to dive into some details. I don't want to talk about every feature here, but some of the features. So let's dive in. If you're interested in getting the details about every feature, I would refer you to the standard. But let's just take a more detailed look at some of the features, the most important ones. So there's the deadline quality of service. Deadline quality of service, and these are all related to timeliness. This is really all about the timing. So deadline quality of service, this policy allows applications to define a maximum period of time to to receive data. And if the application, for whatever reason, does not receive the data before this deadline, the middleware guarantees. So this is, by the way, something that has to be guaranteed by the middleware, that the middleware will inform the calling thread data is not delivered. So this is then the quality of service offered here. And yeah, what could be a reason why data is not delivered on time? Yeah? Might not be there. Yeah. It just took too long. Maybe it was a low priority message and there were too many other high priority messages in the system. Maybe there was a sensor failure and data could not be read from a sensor. Then another quality of service option is latency budget. So this policy then allows applications to say kind of how urgent the data that is sent is. So the latency budget specifies the time period within the middleware must distribute the information. So if you as the publisher want to send a message from A to B, you can tell the middleware, I want you to deliver this message within the next 500 microseconds. So it's like a DHL Express, right? So with DHL Express, you can make sure that that things are arriving on time. We're not talking about microseconds, but maybe about a day. And this way, the sender, that is the publisher, can tell how urgent this data has to be delivered. Any questions on this, by the way, like deadline or yeah? Yeah, that is correct. So in the first case, what's going to happen is you can, for a topic, let's say there's a topic that you send frequently, specify a deadline, and if that deadline is being missed, then the sender, sorry, the recipient is being informed. In the latency budget case, the sender is being informed because the sender requested this. So in one case, the sender requested that, in the other case, the recipient requested that. I hope I'm telling the right thing here because it has been quite a while that I implemented this myself. But the deadline is for the arrival of data. So this is specified by the subscriber, and the latency budget is specified by the sender. And then there's transport priority. And that one then allows applications to control the importance associated with a topic. So very similar to what you've seen with the time sharing aspect of multiple CPUs, that you have for every priority you have a FIFO. This is the same principle here. So if, let's say you have 100 priorities and you have a FIFO for priority 98, and you have three topics in there, and someone else sends another topic, another publisher sends another topic at priority 99, so that one obviously will be handled first. Then some qualities of service with respect to data delivery. Just want to take a look at where I am in terms of slides. I hope I can finish today. But we might have a chance here. Okay. The data delivery. Let me maybe go through this slightly faster so that we can get, actually I'm not sure, maybe I have to ask Stefan to finish the last part. Let's see, presentation quality of service. Here in this case, this quality of service policy gives control on how changes of the information model are presented to subscribers. So this also means that sometimes if your topic is based on an object, you don't need all of the member variables of that object. Maybe you only need one, and so you can specify how things are then actually going to be presented to a subscriber. Then there is the reliability quality of service. That's a policy that controls the level of reliability, and the two choices here are reliable or best effort. So reliable meaning if it doesn't happen, you will get an error message, and best effort basically means do whatever you can to make it happen, but if it doesn't happen, then I don't really care. And this best effort, for instance, is very often being used for communication between real-time system and a non-real-time system. So everything within the real-time system, and this is sort of the transition to OPC UA, everything within the real-time system, you want to be using the reliable feature, whereas if you want to just provide data to the non-real-time system, which obviously is then also not safety critical anymore, you often use the best effort feature. I think I'm going to skip the partition one, and then there's a destination order, and this we talked about that already. So just making sure that the ordering according to source and destination timestamps, and here the emphasis really is on timestamps, is going to be the same for a given topic. And then the last one, ownership quality of service policy. We talked about that already. If you have the motor controller as a subscriber, you only want to receive data from one and only one publisher. So you can have some exclusivity there. Yeah, that much about quality of service. As I mentioned, there are many more. So we only talked about a couple of them. Yeah. To be honest, I would have to look up the documentation to give you the. So I'm not fully confident with my reply, but if I'm not mistaken, you can. So by default, if you do not set any policy, then a publisher sends a message and it can be received by every subscriber. You can also use a policy, but I think that's if I'm not mistaken, it's a different policy. It's not this one. There's another one where subscribers can claim I'm going to own this, and what publishers then can say, my message can at most be received by n subscribers. And that's another quality of service. So this n can be 1, so that would basically be exclusive. But it can also say there's a maximum of 5, and the reason might be if it's more than 5, there's too much compute time being used, because every time your message is received, it triggers some algorithm that computes something that takes CPU time, and then you run out of time eventually. And so you as a developer then can say 5 is the number, only 5 clients, or maybe for the sake of redundancy, you want to limit it to 2 or 3 to make sure that your system remains up and running. But to be frank, I would have to read up the documentation to give a certain answer. I have about 50 slides talking about that, and I was But I don't. I think we'll have to. I'm really unhappy about that because I would have loved to talk about that. Maybe we can start going into this, and then Stefan will continue with this next week. I'm going to jump ahead very quickly just to give that example. So here in this case, we consider 4 processes, no matter whether they are local or distributed, with different states. And this now is related to synchronous message passing, which is the mechanism implemented on DDS under QNX. Different priorities, and now we're going to see how all of these work together. So you have this guy up there, a subscriber, like one subscriber, and then you have multiple publishers working with different priorities. And this example, this is about 50 slides going through a very concrete scenario where exactly what you were just asking. You have the subscriber is still working on something, and then the higher priority publisher sends something, and how does this actually work in terms of scheduling? And how the question then also is, how do you do this not only in a local system but in a distributed system? But I'm afraid that I won't be able to finish that in 4 minutes, so let's quickly summarize with these 2 slides, and then I'm going to describe the scenario, and Stefan then will next week walk you through that example. So to summarize, and to give an overview of DDS features once again. So it's a standard-based publisher-subscriber middleware, very low latency, predictable data dissemination. It really is scalable. So even if you have a few 100,000 or even a few million nodes or topics, the system will be able to handle this. Stability over overload. This was the example that I mentioned. You have the 2 high priority, like one high priority topic, like one publisher, one subscriber, and then a large number of low priority topics. CPU load 100%, but the high priority stuff is not at all affected by this. So you want to be stable under overload. Scalability, obviously you want to be able to set policies, quality of service policies, to control latency and throughput. Actually, at the end of the slide deck, you will see some sample measurements, some typical numbers that are typical for DDS. They were not measured with DDS, but just to kind of give you an idea what typical numbers for latency and throughput are in real-world applications with local communication and also distributed communication. High performance persistence, and then obviously event-based processing. And events can be manifold, obviously. Can be as simple as adding a new subscriber. So now to prepare you for the example that that Stefan will talk about next week. Within many DDS implementations, and specifically with the ones that run on QNX, the topics and specifically the data is being exchanged through synchronous message passing. Synchronous message passing is a method. So every one of you who was in the real-time systems class in the summer term knows this already. The idea here is that you have 4 different process or thread states, and these are ready, send blocked, reply blocked, and receive blocked. And if you now as a sending thread, you want to send a message, so you're in the ready state, you call the command message send, so you want to send data from A to B. Then you're going to be send blocked, and you will be send blocked until your recipient, and I should also say sender and recipient is middleware is either the sender or the recipient, and then the publisher or subscriber is going to be the recipient or the sender, respectively. And so you're going to be send blocked until your partner calls message receive. Then you're going to be reply blocked. And so that means now your partner has received the message, can process it, can generate an answer. And at some point, your communication partner will reply, so it will send the answer to you through the command message reply or message error if something went wrong. Maybe you provided wrong data or something else went wrong. And you're going to be back in the ready state. If you are the receiving process or the receiving thread, you will call message receive. You're going to be receive blocked. And then at some point, the sender will send out the message. And the moment he did that, you will be in the ready state again. You have the data available, and then you get the CPU back and can keep running. So this is these are the state transitions for synchronous message passing using these 4 states. And oh, sorry, obviously there's the message reply as well. So once you've received the message, you're going to work on that, and then at some point you're going to call message reply so that the sending thread can then change its state from reply block to ready. And using this principle, we're now going to see next week an example with 4 processes or 4 threads with different priorities. And we will see how the scheduling works and how priorities are being inherited. And the principle that that you will see there is a principle that then allows for the ability to give timing guarantees in a global way. So not only locally, but even if you have a network of multiple nodes, and you have a very high priority process, highest priority process in your system, higher than everything else in your entire network. And if this process now wants to send a high priority message to someone else in the system, you want to make sure that on all of the nodes that are being involved in this communication process, that this message gets handled before everything else. And we will then see, using this example, how this can be implemented locally and globally as well. Okay, I exceeded the time by 2 minutes. I apologize for that. Thank you so much for your attention, and then I will see you again in 2 weeks.